Imagine, you're sitting in your favorite cafe, sipping a steaming latte, scrolling through photos on your phone, or laughing with friends about a new movie. Everything is peaceful like any other day. But then, in 120 seconds, all life on Earth could be wiped out. Not centuries, not hours, just 2 minutes. Science has proven there are disasters powerful enough to erase humanity faster than you can scream, "What's happening?" The following 3 terrifying events will make you shudder because they're not fiction. They could happen at any moment, and Earth will never be the same. Earth stops spinning. Our planet races through space at a rotation speed of 1,600 kilometers at the equator. If it suddenly stops, everything on the surface, houses, forests, oceans, will turn into rubble in an instant. A gamma ray burst from space. A deadly beam of light from a collapsing star, with energy billions of times that of the sun, could incinerate life in seconds. An asteroid collision. A 50-kilometer cosmic rock hurtling at 100,000 kilometers, powerful enough to knock Earth off its orbit and plunge it into eternal darkness. We will analyze every second of these disasters, so you can see how quickly and brutally the apocalypse could strike. But before we start, subscribe to the channel now and hit the notification bell to never miss cutting-edge scientific discoveries like this. Ready? Let's count down 120 seconds to the end of the world. Part 1. Earth stops spinning. Earth spins on its axis at a speed of about 1,600 kilometers at the equator, completing one rotation every 24 hours. This motion not only creates the day-night cycle, but also maintains the stability of the atmosphere, oceans, and weather patterns. The centrifugal force from the rotation causes Earth to bulge slightly at the equator, affecting local gravity. More importantly, the Coriolis force, an effect of Earth's rotation, shapes ocean currents and wind patterns, from tropical storms to jet streams. If Earth suddenly stops spinning, everything on the surface would retain the inertia from the previous motion. Imagine you're on a bus going 100 kilometers and it stops abruptly. You'd be flung forward. Now, multiply that effect thousands of times, applying it to everything: people, vehicles, buildings, oceans, and even the atmosphere. Additionally, the loss of centrifugal balance would cause massive geological vibrations, triggering earthquakes and volcanoes worldwide. What could cause Earth to stop spinning? In reality, this is almost impossible because it requires an immense force to cancel the planet's angular momentum, approximately 2.68 or 10 to 29 Celsius. However, science fiction hypotheses include a collision with a massive celestial body, the impact of an alien super technology, or an unprecedented physical event. Whatever the cause, the consequences would be a chain of domino disasters unfolding in an instant. Events by second, 120 seconds. Seconds. Earth suddenly stops spinning. No one notices immediately because humans don't perceive the planet's normal rotational motion. But beneath the surface, Earth's crust begins to endure tremendous pressure as the momentum of the core and mantle collides with the stationary crust. Seismic sensors worldwide detect abnormal vibrations, but no warnings can be issued in time. 10 seconds. Inertia causes everything on the surface to continue moving at its previous speed. At the equator, supersonic winds reach 1,600 kilometers, stronger than any hurricane ever recorded. The strongest hurricane, Typhoon Haiyan, reached only 315 kilometers. Trees are uprooted. Vehicles fly like toys, and low-rise buildings are torn apart. At higher latitudes, wind speeds decrease, 800 km at 45 degrees latitude, but they're still enough to cause severe damage. The atmosphere, which was also rotating with Earth, creates chaotic jet streams, disrupting all weather patterns. 30 seconds. The oceans, less restrained by friction than land, begin to form colossal tsunamis. On western coasts, where inertia pushes water, waves 2 to 3 kilometer high crash, submerging cities like Los Angeles, Tokyo, or Sydney. Earthquakes of magnitude 10 to 12 spread due to the sudden compression and expansion of Earth's crust, destroying bridges, roads, and even the best earthquake-resistant structures. The atmosphere becomes chaotic, with supersonic storms forming across every continent. 60 seconds. The loss of centrifugal force causes gravity at the equator to increase slightly, about 0.5%, making objects temporarily heavier before being swept away by winds. Volcanoes begin erupting due to changes in mantle pressure, releasing millions of tons of SO2 gas and ash. Temperatures begin to polarize. On the side facing the sun, continuous light pushes temperatures to 100 degrees within minutes. On the other side, darkness causes temperatures to drop to a 50 degrees Celsius in many areas. Billions of people have no time to react, swept away by winds, tsunamis, or killed by collapsing buildings. 90 seconds, major cities are almost flattened. Shockwaves from winds and earthquakes travel thousands of kilometers, destroying even the sturdiest structures. The oceans continue to surge, flooding low-lying areas. The atmosphere is severely disrupted, with clouds of dust and toxic gases blanketing the sky. In polar regions, the impact is less severe due to lower rotational speeds, but earthquakes and climate chaos still make survival difficult. 120 seconds. Human civilization collapses. Only a few organisms underground or in deep bunkers might survive temporarily. Temperatures swing to extremes. The lit side melts at 150 degrees. The dark side freezes at 100 degrees. The atmosphere becomes a toxic mix of dust, SO2 gas, and superheated water vapor. Earth enters a deadly era where surface life is nearly non-existent. Long-term impacts. If Earth completely stops spinning, the planet could become tidally locked with the sun, with one side always lit and the other always dark. This creates a harsh environment, with life only potentially surviving in the twilight zone, the boundary between light and dark. However, before reaching this state, weather and climate cycles would collapse entirely. Volcanic ash blankets the sky, causing a global winter lasting decades. The oceans would stabilize in a new state, but marine ecosystems are destroyed by tsunamis and chemical changes. Only bacteria and some anaerobic organisms underground have a chance of long-term survival. Part 2. Gamma-ray burst. A gamma-ray burst, GRB, is one of the most violent events in the universe, occurring when a massive star collapses into a black hole or two neutron stars collide. GRBs release energy equivalent to 10^44 joules in a few seconds, billions of times the energy the sun emits over its lifetime. If a GRB occurs within a few thousand light-years and is aimed directly at Earth, the gamma-ray beam would arrive with virtually no warning as it travels at the speed of light. Gamma rays are the highest energy form of electromagnetic radiation, capable of penetrating matter and destroying molecular bonds, especially DNA. A sufficiently powerful GRBY would incinerate the atmosphere, destroy the ozone layer, and trigger chemical reactions producing toxic gases like NO2. The immediate impact is mass death, followed by ecosystem collapse due to unfiltered UV rays from the sun. The probability of a dangerous GRB hitting Earth is extremely low, about once every billion years in our galaxy, but its consequences are unimaginable. Scientists suspect a GRB may have contributed to the mass extinction 450 million years ago, Ordovician period, when the ozone layer was destroyed and surface life nearly vanished. Events by second, 120 seconds. Seconds. A gamma-ray burst from a star collapsing 5,000 light-years away strikes Earth. There's no warning, as the radiation travels at the speed of light. In 0.1 seconds, the hemisphere facing the GRB absorbs energy equivalent to 1,000 nuclear bombs per km. The radiation destroys the DNA of all surface organisms, from humans to bacteria. 10 seconds. Temperatures in the affected hemisphere spike to 500 to 1,000 degrees, igniting forests, evaporating surface water, and incinerating anything exposed. Humans, animals, and plants on continents, like the Americas, Africa, or Asia depending on the GRB's direction, die instantly from radiation and heat. The atmosphere is ionized, creating a blinding light like a supernova explosion in the sky. 30 seconds. The ozone layer, which protects Earth from UV rays, is completely destroyed within the first 10 seconds. Chemical reactions in the atmosphere produce NO2, a toxic brown-red gas, causing suffocation and turning the sky blood red. Firestorms spread across continents due to high temperatures, destroying cities and ecosystems. In the hemisphere not directly facing the GRB, the initial impact is milder, but the sky glows from reflected light. 60 seconds. Shockwaves from the heated atmosphere spread at 10 km/s, demolishing structures within thousands of kilometers. Global temperatures fluctuate wildly, with affected areas reaching 2,000 degrees Celsius at some points. The atmosphere becomes unstable, with electromagnetic storms and supersonic winds forming due to pressure differences. Surface life in the irradiated hemisphere is almost entirely eradicated. 90 seconds. Unfiltered UV rays from the sun, no longer blocked by ozone, begin incinerating surviving life. Marine organisms in shallow waters die en masse due to UV radiation penetrating the water. Toxic NO2 gas spreads, causing suffocation in densely populated areas. In the unaffected hemisphere, people begin noticing the disaster through abnormal phenomena: a red sky, rising temperatures, and disrupted radio communications. 120 seconds. Surface life in the irradiated hemisphere is eradicated. The global atmosphere destabilizes, with clouds of dust and toxic gases blanketing the sky. Temperatures swing from 100 degrees Celsius in hot zones to 50 degrees Celsius in shadowed areas. Earth becomes a planet without protection, with life only temporarily surviving in deep oceans or caves. Long-term impacts. After 120 seconds, Earth enters a radiation winter phase. Without the ozone layer, UV rays from the sun eradicate remaining surface and shallow ocean life. Toxic NO2 and other compounds pollute air and water, causing widespread death. Global temperatures drop due to ash from fires blocking the sun, leading to a decades-long global winter. Ecosystems collapse, with food chains broken from the lowest levels, algae and bacteria. Only a few organisms in deep oceans or underground might survive, but they too would eventually die out due to lack of solar energy. Part 3. Asteroid collision. An asteroid 50 km wide, traveling at 100,000 km/years. Striking Earth would release energy equivalent to 10^24 joules, 10 billion times the largest nuclear bomb ever tested. For comparison, the Chicxulub asteroid, 10 km wide, 66 million years ago caused the extinction of dinosaurs, and a 50 km asteroid would be thousands of times more powerful. Such asteroids are rare in the solar system, but interstellar objects like Oumuamua or fragments from the Kuiper Belt could carry this size. The impact would include an initial explosion, creating a crater hundreds of kilometers deep and incinerating everything within 5,000 km. Shockwaves spreading globally. Ash blanketing the sky. An orbital disruption, shifting Earth's position. Additionally, the asteroid's gravity would trigger earthquakes and volcanoes even before the collision. Modern radar, like NASA's DART, can detect asteroids from afar, but if one comes from the sun's direction or interstellar space, the warning time could be mere hours or none at all. Such a collision would be a global catastrophe, with no surface organisms having a chance of survival. Events by second, 120 seconds. Seconds. A 50 km asteroid hurtles toward Earth at 100,000 km. Radar fails to detect it due to its approach from the sun's direction. The asteroid's gravity begins disturbing Earth's crust, causing magnitude 10 earthquakes in many areas. 10 seconds. Earthquakes spread, with cities near the impact site, assume the Pacific Ocean, collapsing entirely. Volcanoes erupt simultaneously from Yellowstone to Vesuvius, releasing billions of tons of lava and ash. The sky blazes as the asteroid frictions with the atmosphere, creating light brighter than the sun. 30 seconds. The asteroid strikes Earth, creating an explosion with the energy of 10 billion Hiroshima bombs. The impact crater is 500 kilometers wide, 50 kilometers deep, incinerating everything within 5,000 kilometers. Temperatures at the impact site reach 10,000 degrees Celsius, vaporizing rock and seawater. 60 seconds. Shockwaves spread at 20 km, leveling all structures globally. Firestorms spread across continents with temperatures of 2,000 degrees Celsius in many areas. Ash and debris shoot into the atmosphere, blocking the sun, causing global darkness. 90 seconds. The atmosphere is largely destroyed, with oxygen consumed in fires. Global temperatures plummet due to ash, dropping to 50 degrees Celsius in many areas. Earth trembles. Its orbit shifts by about 0.1 degrees, disrupting seasonal cycles. 120 seconds. Surface life vanishes. The remaining atmosphere is a toxic mix of CO2, SO2, and dust. Earth plunges into darkness, with temperatures dropping to 200 degrees Celsius in many areas. Only a few bacteria in deep oceans or underground have a chance of survival. Long-term impacts. After 120 seconds, Earth enters a nuclear winter lasting thousands of years. Ash blocks the sun, preventing photosynthesis and destroying food chains. Global temperatures drop to 100 degrees in many areas, with ice covering continents. The atmosphere destabilizes, with dust storms and acid rain persisting. The orbit shift could move Earth closer to or farther from the sun, exacerbating harsh conditions. Life, if any, survives only in hydrothermal vents at the ocean floor, but even these would eventually run out of energy.